Recording started.
All right. Hi, Science 10 students. Here's the recording that's going to help prepare us for the test, first test coming up in a little bit. So we're going to just talk about the periodic table a bit. And so as you can see, I think we mentioned this before, I'm not sure if we did, that the different columns stand for the number of valence elements. And you guys remember that the number of valence elements, or sorry, I'm trying to say valence electrons. The valence electrons are the only electrons that actually take part in chemical reactions, right? And those are the outer electrons. And so, again, we kind of skip over the transition metals. Those ones are a little more iffy. They have two different charges in the periodic table. And so we just number these columns here. So if you can just remember how to number these columns, those will tell you the number of valence electrons for each group. Okay, so guys, please know the different groups, these particular groups, 4 different groups, and know what the names are. Okay, so alkali metals, since it's a +1 group, they form +1 charges. And since group number 2, or column 2, the alkali earth metals, they form +2 charges. Then when you go over to group number 7, they form -1 charges. And you can see those charges on the periodic table, right? You see the little minuses in the box or the little pluses sort of thing. And of course, we know noble gases, they don't usually react, right? Okay, so that's just kind of a little bit of an overview. And so we're going to skip this page here. So let's just go over these questions here. For each of the following, state the name of the group and the charge on ions formed from elements in that group. So if you can remember these, Matthew, go for it. You know, group 1, group 8. Otherwise, we'll go ahead on the next page, but just feel free to jump in there if you can remember some of those. So we're looking for group 1, the charge on it, and when it forms ions with other elements, and the same with group 8. And then for each of the 2 groups, state the number of electrons in its valence level. Whoa, sorry, I just had an update from my computer pop up here, just kind of distracting me for a sec. Okay, so we'll just kind of review what these are then. So group 1, again, is the alkali metals, and group 8 is the noble gases. And the charges, as far as the charges, or rather the number of electrons in the valence level, it's going to be 1 for group 1, it's going to be 8 for the noble gases. All right? And that all goes back to the numbering system we use, where we put 1, 2, 3, all the way to 8. Okay? And so, going on to the next one, this here is showing us a basic chemical reaction, right? And as we know, there's reactants going to products. Okay, so again, these guys are called reactants, these are products, and it makes sense, right? Because these substances are reacting together. That's why they're the reactants. If we look at the next question here, it says name the reactants and products. And I guess I've already done that. I meant to erase it and put it on the next page, but I've already got it done here. So the reactants are propane and oxygen, and the products are going to be carbon dioxide, water, and heat. Hey there, Aiden. How's it going today? Hey, I'm doing well, thanks. So have you guys, did you guys by chance hear about this finding where these guys in Europe possibly have found that the light can travel faster than the speed of light that we currently think of? I think the current speed of light is supposed to be like 32,000, I think it's meters per second. And now they think that light can actually travel faster than that. Have you guys heard about that? If that's true, then that's like really big as far as science, eh? Because it's like breaking Einstein's, you know, some of his contributions to science. But they took some not neutrons, neutrinos, these particles, and they shot them through the Earth, and they came the other side. They came more quickly than they would have predicted at the current speed of light. So anyways, I thought that was kind of cool. I always think it's bizarre how light is so fast that it goes around the Earth about 7.5 times each second. So that just boggles your brain. And if you think about light years, when they talk about light years, that's how far light travels in a whole year. So anyways, I know I'm getting a little off topic, but I was just kind of curious if you guys heard about that. Okay, well, we'll just move on here, guys. We were just talking about what chemical reactions are as far as reactants and products. So that's what we were reviewing on this page. And we'll just go on to the next page. You guys remember all this stuff about exothermic and endothermic? So exothermic reactions, they produce or release heat. In other words, the environment gets more hot with an exothermic reaction. The way I always remember it is I think of the EX part of it, and I think heat exits. In other words, it leaves the chemical reaction, it's produced by the chemical reaction, and as long as I know what exothermic is, I know what endothermic is. So of course, an exothermic reaction, if you've got some sort of combustion reaction, you got a heat explosion going on, that's exothermic. I don't know if you guys have, you've probably messed around with, vinegar and baking soda before, right? I know I used to do that all the time. But did you know that if you take vinegar and baking soda and you get that chemical reaction going, did you know that it absorbs heat from the environment and your hand's actually colder if you do that chemical reaction? So if you haven't tried it before, check it out. It's kind of cool, no pun intended. So anyways, that's the difference between exothermic and endothermic. And so here's a picture, of course, showing an exothermic reaction where heat's produced. So could somebody help me here with filling in these blanks? So the combustion of coal does what to energy? What word would we put in here to describe the energy change that happens with the combustion of coal? Okay, it's exothermic. So the second blank would be exothermic. And then does an exothermic reaction use up energy or does it release energy? What would we put in the first blank there? Okay, it's going to release or produce energy, right? Good. Okay, so we're going to talk now about physical and chemical changes. So remember, with the physical change, you just have a change to the size of an item or the state of the substance. So for instance, if you take some glass and you just break it, that's a physical change. You haven't really changed the glass at all, right? Same thing if you change water from liquid water to ice or steam, you haven't actually changed its properties. It's still water, right? Okay, so those are all examples of physical changes. Whereas chemical changes involve something new being produced, and you can sense that something new by, there's a color change or maybe a gas being produced. So examples of chemical changes are cellular respiration, where sugars are burned by cells, right? Another thing is bacteria use fermentation, right? That's another kind of chemical change. And that for them produces energy. So they do that just like humans use cellular respiration. So see if you can classify each one of these as either a physical or chemical change. What do you think? Combustion, is that a physical or chemical change? You just put a C or a P. Okay, good. That's chemical. How about ice melting? P or C? That's physical, yeah. And fermentation? That's going to be chemical. Good stuff. Right on. Okay, so now we're talking about the law of conservation of mass. And so I wrote, don't break the law of conservation of mass. So what is this law again? Okay, so what does it mean to conserve mass? Well, basically it means in any chemical reaction, the mass of the reactants are going to equal the mass of the products. In other words, we don't lose anything when we do chemical reactions, right? Nothing gets lost. So when you have carbon plus oxygen producing carbon dioxide, if you add up the 12 grams and 32 grams of the reactants, it's going to be 44. And then that's the same amount as the carbon dioxide products. Okay? So that's what it means by the conservation of mass. Sometimes they call it the conservation of matter. Okay, so when we say that matter is always conserved, we're saying that the mass or the weight is going to be the same thing on both sides of the reaction. It also means the number of atoms is the same before and after as well. Okay? So this one's probably too easy because I just told you, right? What two quantities always remain the same? So that's going to be the mass and the number of atoms. Okay. So what we'll do at this point is just kind of review the different types of chemical reactions. So first of all, we got the combustion reaction, right? I just noticed Aiden was typing something there. I think, unless something's just playing tricks here, that could be as well. Okay, yeah, sometimes these things just come up, and I'm not sure where they come from. Too funny. Okay, so with combustion reactions, usually they involve hydrocarbon substances, so they have both carbon and hydrogen, right? And then, of course, you need oxygen, right? And it always produces water and carbon dioxide. Okay, so that's hydrocarbon or combustion reactions. Formation reactions, just like the name suggests, you have two things going together to form something else. Okay, and here's an example. So two elements often form a compound. That's formation. Decomposition, when something decomposes, it's kind of the opposite, right? Compounds are breaking down. So X and Y go to X plus Y. So here's an example. You've got a compound decomposing into the elements that make it up. Single replacement reactions. Here's where it gets a little more interesting, because you've got an element plus a compound producing another compound and an element. But see, what happens here is the element that goes with this one, you get BX, that B gets switched with the A here. So now you have AX. And now the B that was here becomes an element on its own, right? So you're just switching out one of the elements from the compound for the one that was there before. Okay, so looking at this example here, you can see that we have HCl, but now the Zn replaces the H, and so we have ZnCl2. And now you have H on its own. Okay, so that's a single replacement reaction. And then, of course, there's the other one that's quite similar, which is a double replacement. This time, two things get swapped. So this time, the W and the Y are both getting swapped. Both compounds are swapping one of their elements. So they're either swapping their first element or their second element. Okay, so you can see here what's going on is this K here is now going to combine. It's going to take the place of the H. So you have K2SO4. And the H that was here is going to combine with the OH, and that produces HOH, also known as H2O, or water. Okay? So, see if you guys can state which each of these is in number 6 here. So, if you want to just put the first few letters, so what do you think this first reaction is? What type? You've got a compound. So what do you think could happen with that compound? Pretty much just break down, eh? That's pretty much the only thing that could happen. So decompose, decomposition reaction. How about this one? That one would be a combustion, right? This one, we've got two elements going together to produce or form, right? So it's going to be a formation reaction. This one, you can see you have two different elements forming compounds. So whenever you have two compounds, you know it's going to be a double replacement, whereas if you have a compound and an element, it's going to be a single replacement. Okay? So next question. State whether the reaction below is exothermic or endothermic. So just say, EX or EN. And then state whether it's a single replacement or a hydrocarbon. Okay, well, we know if it produces energy, it's going to be exothermic, right? And we know it's a hydrocarbon, right, or a combustion reaction. because it's burning in oxygen. Okay, so let's go on to the next one. This just has all the answers for those ones at the top. And yeah, so we've got this page. All right, so at this point we're going to talk about how do you predict the products of a reaction. So let's say you have a reaction where we know that these two things are combining together or reacting together. How do you know what's going to be produced? Well, the question is telling us it's a single replacement, right? So we know that this Cl is going to take the place of this. We know it's going to take the place of the Br because Cl and Br are in the same column in the periodic table, right? So it makes sense they're going to react the same way. Makes sense that Cl is not going to take the place of Al. Okay, so we know it's going to be AlCl something, but we don't know what the exact compound is. We're going to have to figure that out. And then we know that Br is going to be on its own, but again, we don't know exactly what it looks like. So those are the two things we need to figure out. So let's figure out what compounds we get. So we know, again, that Al and Cl are reacting together. We know when we look on the periodic table, it's Al plus 3. We get that from the little square for Al. Cl is -1. And again, when we form compounds, we just switch the elements. So the 3 that was with the Al comes down here. The 1 with the Cl comes here. So we have Al1Cl3, which is the same as AlCl3. Okay, so we know that that's the compound that's going to form. So what is the Br going to look like? Do you remember what diatomic elements mean when we say that the elements that are in the second last column are diatomic? What does the di part mean? What does the number di? What number does di usually stand for? It's 2, right? Okay, so because of that, because Br2 is in the second last column, all of those guys, those gases, halogen gases, are diatomic. Okay, so that's why we know that it's going to be Br2, not just Br. All right, so here we have another question that's kind of like that, finding the product that's going to be formed. And so we have sodium and iodine. So what product is going to be formed? Well, we have to look on the periodic table, right? I should have put these charges up above. Somehow they got below. But anyways, we know we cross the charges, so we get them like this, and then we just get rid of the numbers, and so it's NaI. So that's going to be the product that's formed. So that one wasn't too bad. All right, so this one's a little more tricky. This one takes some more thought. So it says when solid sodium metal is exposed to nitrogen gas, and it tells us that nitrogen is also diatomic. Okay, so even though N is not in the second last column, it's also diatomic. So that's important to know. It says a rapid reaction occurs. The only product of this reaction is a solid white powder. Okay, so let's figure things out here. Well, we know that sodium metal is exposed to nitrogen gas, which is diatomic. So sodium is Na, so far it could be any one of these answers. But since it says that nitrogen gas is diatomic, that means N2, right? Okay, so it can't be A, so we know that so far. We know that there's a powder produced, so in other words, the powder is produced by Na and N reacting together. So we have to think of their charges and figure out what compound is going to be formed. So we'll look on the next page. When we look on the periodic table, we see it's Na plus 1 and -3, so we cross those charges to get this, and we get rid of the 1, so it's Na3N. Okay, so we can see that the answer is going to be C. So even though this question is saying, you know, what's the balanced equation, we actually don't even need to know what the balanced equation is because this is the only one that has Na3N, which is the correct compound. Okay, we could check though, since it's saying balanced equation, we could check and we see, you know, 6 Nas on this side, Na3, and 3 times 2 is 6, so 6 Nas on this side, 2 Ns on this side, and we have 2 times the N here, so 2 Ns. So everything balances out. Okay, so again, we didn't need to know the balancing part of it, but you know, we can check that later on, and it's good to know. Because you know, if you do have any questions on balancing, that's one way you can check out if it all works to see if the number of atoms are the same on both sides. Okay, So now we're going to talk about moles and mass. Now, I remember when I was taking chemistry in high school, I used to do chemistry with a friend of mine. He always kind of found this moles thing really different, you know. Here's the way I think about it. A dozen is just like 12 of anything, right? Whether it's a dozen donuts or Smarties, doesn't matter, right? So a mole, instead of being like 12 of anything, is 6.02 times 10 to the 23 of anything. So it doesn't matter if it's donuts or Smarties or atoms or molecules. We're normally talking about atoms and molecules. But, so in other words, it's just a really big number. That's all a mole is. It's just always this many of something, no matter what that something is. Okay, so I just got a little cute little cartoon here. It's got a mole. Looks like the animal, the mole, and he's writing out the number here. So that's a huge number, though, isn't it? Eh? I mean, that's ridiculous. It's not as big as a Google, of course, but it's big. Okay, so what we'll talk about now is the atomic mass. And so what is atomic mass? Well, it's the mass in grams of 1 mole of an element. So if you look on the periodic table and you see this number here, remember this is the atomic number up here, this is the atomic mass. This number, 65.39, stands for how many grams 1 mole is of zinc, okay? So 1 mole is this many grams. Okay, so we have to know how to do calculations to go from mass to moles and from moles to mass, right? So if we're going from moles to mass, if the question says, how much mass is 1 mole of carbon dioxide, you have to look on the periodic table, and you have to look at the number, the atomic mass for carbon. You see it's 12.01. You look for oxygen. See, for oxygen, it'll just give it for 1 O, but there's 2 O's here, so we have to multiply by 2. Okay? So it's 12.01 plus 32, and that gives us a total of 44.01 grams. Okay, so that's 1 mole of carbon dioxide. All right, so that's how you go from mass to moles. Now, here's another question that goes from mass to moles. If you had 65.74 grams of carbon dioxide, how many moles would you have? Well, first thing is to get an idea of approximately how many moles you have. Like, do you have more than 1 mole or less than 1 mole? So you remember from the last question that 1 mole of carbon dioxide is 44.01 grams. So first of all, we figure out what 1 mole is, right? Using the way we did in the last question. And since 65 point whatever is greater than 44, we know we have more than 1 mole. So we expect we're going to get an answer that's more than 1. So the way we do it, we take the mass that we have in the question divided by the mass of 1 mole, and that's going to give us the number of moles. So here it gives us 1.49, almost 1.5. Okay, so that's the important little equation you need to know. The mass that we have divided by the mass of 1 mole equals the number of moles. All right, so we just went from mass to moles. Let's go from moles to mass. Okay, so it says how many moles are there in this many grams? Okay, this is actually a similar question to the last one. Maybe we won't go through this one. You can practice it later on, because this is actually a similar question to the last one. So again, we do the same steps, and we're going from moles, from mass, and figuring out how many moles that is. I won't go through this because we just went through the really similar one. Okay, so now we're going to go from moles to mass. Okay, so what we do in going from moles to mass, we find the mass of 1 mole. In other words, we find on the periodic table that number, that atomic mass, right? Then we multiply that by the number of moles that we're given. So, okay, so in this question, we're going to talk about 3 moles of copper. So, again, since you're doing grams per mole, that's the number you get from the periodic table, and you multiply by moles, you can see that moles cross out on top and bottom, and that leaves you with grams. Okay, so that's how you can calculate grams. You multiply these 2 things together. So when we find the mass here, we're going to find the grams per mole of copper from the periodic table, then we're going to multiply it by 3 moles of copper, and that's going to give us the number of grams of copper. Okay, so from the periodic table, we would find it at 63.55 grams per mole. We multiply that by 3 moles, that's how many we have, We see moles cross off on top and bottom, and we're left with grams. 3 times 10 to the 3.55 is this many grams. Okay, so does that make sense, guys? Right on. And really good to practice these later on. Okay, now when you hear the term molar mass, what does that mean? The molar mass of a substance. Well, if you just kind of think about it, it's the mass of 1 mole. That's what molar mass means. Okay? So if the question said find the molar mass of bromine, we need to find the mass of 1 mole of bromine. Okay, so to find the mass of 1 mole of bromine, we know that bromine is diatomic, Br2. So if we look on the periodic table and we see that 1 mole of just Br is 79.9, then 1 mole of Br2 is going to be 79.9 times 2. Okay? So that's how many grams you're going to have per mole, per 1 mole of bromine. Okay. So now we're just going to briefly go over the difference between ionic and molecular compounds, how you name them. You guys remember that when you have a molecular compound like CO2, the little 2, the subscript, affects the naming, so you make it carbon dioxide because of the 2, whereas if you have an ionic compound like calcium chloride, the 2 doesn't affect it, so it's not calcium dichloride. So again, how do we remember or how do we recognize whether we have an ionic or molecular compound? Ionic compounds are metals from columns 1 or 2, in other words, left side of the table, combined with non-metals, which are found on the right side of the table. Molecular compounds are non-metals plus non-metals, which are both on the right side of the table. So that's how you can know just by looking at it that it's ionic or molecular. Okay, so anyone want to take a stab at naming the first one here, MgCl2? Magnesium chloride, that's right, because it's ionic, so we don't make it dichloride. How about this one? Okay, now remember, actually, this one here, we would need to have a metal in order for this to be ionic. So because we don't have a metal, because carbon is not considered a metal, at least for ionic compounds anyways. So because of that, it's a molecular compound, so the 4 is going to affect it, and so it's going to be carbon tetrachloride. Okay? So again, we just consider the metals the first 2 elements when we're naming these compounds. The first 2 groups of elements, that's what I meant. Okay, so we got those ones taken care of. And so now we're going to talk about the unique situation where we have transition elements, so those elements that are kind of in between the left and the right side of the periodic table. Now remember, if you have something like magnesium 4 oxide, remember that magnesium 4 oxide does not tell you that you have Mn4O or MnO4. So it doesn't tell you anything about what the compound looks like. What it tells you about is which ions went together to form the compound. Because remember, with something like, did I say magnesium? Manganese? With manganese and those different transition elements, remember they can have 2 different charges, right? You can see those on the periodic table. So what magnesium 4 oxide means is that we're using the Mn+4 version of the ion to form the compound. So to form the compound, we use Mn+4, and we know that O is -2, so we cross these and we get this. And then we want to simplify it, so we divide 2 into each, and it becomes Mn1O2, or just MnO2. Okay, so again, looking at this compound here, you'd have no clue that that's manganese 4 oxide, because it all has to do with the original ions that formed it. So you would have to go back and try out the ions and see which one produces it. Okay, like if it told you that this is manganese 4, then you would have to go backwards sort of thing. Okay, so that's Roman numerals and transition metals. So this one here is just saying what's the correct formula for lead-4 sulfide. So again, we just have Pb plus 4, S minus 2, and it's the same deal. Okay, so again, I'm just giving you a few more chances to try different you know, like the same kind of question we just went over, but a little bit different. Okay, so remember too, guys, that when we talk about common names in chemistry as opposed to systematic names are the chemical names. A common name is something like water. We just call this water, right? And so the common name for ammonia is NH3, and the common name for hydrochloric acid is HCl. So these are some good ones here to know for the test, okay? Ammonia and hydrochloric acid. Of course, hydrochloric acid, it breaks down our foods in our stomach. Okay, so switching gears here. We're going to talk at this point about atoms and the 3 particles that make them up. And I always kind of think of, like, you know, planets and like the sun, you know, how planets revolve around the sun. Always reminds me of atoms. And of course, the mass of a neutron and mass of a proton are quite close in weight, right? They're close to each other, whereas the electron is tiny, tiny, tiny. It's almost massless compared to these guys, right? So the atomic mass of any atom is just made up of the protons and neutrons. You just ignore the electrons. Whereas the atomic number is the number of protons or electrons, and that's the number we get from the periodic table, a smaller number. Okay, so here's a question for you to think about. Finding the mass number, that's another way of saying atomic mass. So if sodium has 11 protons, 11 electrons, and 12 neutrons, what would its mass number or atomic mass be? Okay, 22. Well, remember that the atomic mass only has to do with the heavyweights, right? So it doesn't involve these electrons at all. So it only involves protons and neutrons. So you want to try again? We're close. So if it's only protons and neutrons, 11 and 12, it's going to be 23, right? Okay. Does that make sense? Good stuff. All right, so that's how we do it there. So that was the mass number, or atomic mass. Okay, now here's a question that has to do with finding the number of electrons or protons on an ion. It's hard to say that. On an ion. Okay, so find the number of electrons and protons for each ion below. So if we're given that calcium has an atomic number of 20 and chlorine has an atomic number of 17. So we'll try calcium first of all. Okay, so how many electrons and protons are we going to have when we have this ion here? So let's check that out. Well, we know that if we look on the periodic table, an atom, so not an ion, but an atom, has an atomic number of 20. And of course, that's 20 protons, 20 electrons. If we're going to have a charge of +2, since electrons are negative and protons are positive, we either have to gain 2 more protons or lose 2 electrons, right? But what is it that always takes place in chemical reactions? Is it electrons or protons? It's actually the electrons, okay? So because it's the electrons, you had to have lost 2 electrons, okay? So if you have lost 2 and you now have 18, then you can see that you're going to have a +2 charge because you have 2 more positive charges than negative charges, okay? And then if we look at the next number, so if you've got Cl and it's got a -1 charge, let's figure out how many protons and electrons. Well, the atom would have 17 of each because it has that atomic number. And since we know that it can only be the electrons that are lost or gained, If it's going to have one more negative charge than positive to get an overall negative charge, then we're going to have one electron gained. Okay, does that make sense? All right, we're getting pretty well along here. I think we just got a few more to go. So, okay, we'll talk about acids and bases, and of course acids and bases produce some pretty cool reactions, right, if you put them together, although I wouldn't just go around the house, you know, choosing any old acid and base, unless you want to make something really interesting, but no, not a good idea. Anyways, so here's the acids, here's the bases, and let's just kind of look at their properties. I mean, not that we go around trying out all these properties. For instance, you know, acids taste bitter and acids are sour and bases are bitter. You can think base, bitter, two B's. Of course, many sour candies have acids in them, so that's a way to remember it as well. So that's one thing. The other thing is as far as how they turn litmus. You know, like you've probably seen if you're swimming at a pool, someone comes along. You ever been there when someone's doing a test, like some health inspector's doing a test or something like that? Or maybe just, you know, the people at the pool, whatever. And they put in a litmus paper. And if it turns blue, you know you have a base. And again, that's easy to remember because like base and blue start with a B. Okay, whereas red is when you have an acid. Another thing is with acids, they react with magnesium to produce hydrogen bubbles. That's kind of a cool little test you can do. So some things we're seeing are the same for both of them. Well, actually, there's only one thing that's the same so far, and that's both conduct electricity. Okay, other things are different. So if we had a question that was saying, you know, list the characteristics of each, then we would basically just have to, you know, list these different characteristics. But just know which ones are in common for both, like this here. And then just know things like, you know, bases are bitter, starts with a B. Bases turn litmus blue, starts with a B. And just remember that acids react with magnesium. All right. You guys are pretty familiar with this stuff having to do with polyatomic ions? I'm pretty sure on the test, if I'm not mistaken, I'm pretty sure that I'll be giving you guys a sheet with the names of the polyatomic ions. If not, you can use the one that's in your textbook. I'm good with that. But become familiar with these. It's good to know these. And so, again, remember a polyatomic ion just kind of behaves like it's one ion. Okay, so this whole group behaves like it's one ion. So if we wanted to write a formula for something like sodium carbonate, what we would do is we look at carbonate, see it's here, and we see it has a -2. So it's CO3 with a -2 up above. And the sodium we know is +1. Okay, so if we go on the next page, we can see how that's formed. Sodium +1, carbonate -2. When we switch these ions here, the 2 comes down here, the 1 comes here, and we would sometimes put a brackets around it because the brackets, because this subscript or number applies to the whole thing. But if it's only a subscript 1, then we don't really need it, and we get rid of it. If this subscript was 2, then we would keep the brackets there, or any other number. Okay, so that's the final formula for sodium carbonate. And for the next one, magnesium phosphate. Okay, so we just go on the table, and again we see phosphates -3, magnesium +2. Okay, so we cross them, and you can see this time, because the 2 goes with the phosphate, we have to put brackets around the whole phosphate, okay, to show that that whole thing is taken twice. Okay, so that's how we do those. There's another good or really important polyatomic ion to know, and that's hydroxide. You know, the most common base in the world is sodium hydroxide, but this one says write a formula for calcium hydroxide. So you can see here it's OH -1. Calcium on the table is +2, Ca +2. So there we go, Ca +2, OH -1. We cross them, and again we put brackets around the OH. to show that the whole thing is taken twice because it's a polyatomic ion. Okay, and I think we're almost done. I think this is the last thing. You guys have been great sticking through with this. Doing a lot of stuff. So the last thing, I'm not going to actually go through all this stuff, but I just wanted to point out that it's really important to know these different WHMIS symbols. And trying to remember what WHMIS stands for: Workplace Hazardous Management Information System, I think, something like that. So anyways, yeah, these are really good, you know, if you're working in a lab, to know that this is corrosive, it's going to eat away at your skin. This, of course, you know, flammable, obviously, poisonous, that kind of stuff. But just know those for the test. And I think that's it, guys. So again, just practice the stuff for the test, and you'll do well. And if you have any other questions, you know, from the other lessons that you wanted to just go over at some point, just give me a shout. So, anyways, thanks a lot for coming, guys. Really appreciate it. Thanks for your good participation. Alrighty. Well, hey, thanks again, guys, and have a good one. Talk to you later. Bye for now.